Yay! We're all here. Big crew this week. Welcome to the Weekly Space Hangout. My name is Fraser, Cain. I'm the publisher of Universe Today, and this week we're going to be talking about overturning the BICEP 2 results. The fact that black holes do exist. A new spaceport for SpaceX, 2 Mars missions arriving at the planet, and many more. So, joining me this week, we've got Alessondra Springmann. Hey, Sandy.
Hello. I'm sorry, Judy Schmidt. I do not have cats crawling on me today.
No cats.
No,
and I can't say that you're at the Arecibo Observatory because you are no longer at Arecibo. So where are you? What are you doing?
I'm at the Lunar and Planetary Lab at the University of Arizona working on the OSIRIS-REx mission. It's an asteroid sample return mission to asteroid Bennu.
Sweet.
Bring
it's
pieces
like you were
of it
born
home,
for that
it
job.
turns us into pieces.
So is this how you atone for zapping all those asteroids?
No, we're going to do worse. Now we're going to bring parts of them back.
You're just taking it to the next level. We've got Dr. Brian Koberlein.
Hi. I also have no cats crawling over me.
I could have one soon, depending on whether I've fed her recently enough. Jason Major.
How we doing?
Good.
All my cats are in the next room, so
Yeah.
they will not be crawling all over me either.
Locked away with your telephones.
They're locked away.
Yeah. And Morgan Redford. Hey, Morgan.
Hey, Fraser. Also cat-free.
Good. Well, I'm glad we really got that cleared out, that the presence or non-presence of cats has been really squared away. All right. Well, let's start with 2 missions arriving at Mars this week.
Yeah, this was a big week for Mars exploration. Just about a week ago, on Sunday, the MAVEN mission, which I should mention is operated by my employers, arrived at Mars. It completed its 35-minute Mars orbital insertion burn and achieved a successful Mars orbit. And this is not an easy thing to do because your rocket engine has been sitting dormant in the coldness of space for months, sometimes years, and then you need it to turn on when you ask it to turn on, burn for exactly how long you ask it to burn for, and then cut off. Because if you burn too short, you'll skip on right by the planet, and if you burn too long, you're just going to bore right into it. And MAVEN is not a landing mission. And then just 2 days later, the Mars Orbiter mission, which was the first interplanetary mission of the Indian Space Agency, completed basically the same process. And they also have achieved a successful Mars orbit and will begin their science operations as well. And even though it's been less than a week, both of these missions have returned pictures. I don't know if you have those pictures. I can put it up here.
See if handy. I can.
I have it. Let's just see if I can. See if
well, you just keep talking. I'll work on getting.
All right. How about that? Can you see that?
Yeah.
All right. So this is a picture. The first picture taken by the ultraviolet imaging spectrograph on MAVEN. And so MAVEN, unlike most missions, doesn't have a camera on board. Because, as I've been told over and over again, if you put a camera on board, you're going to be tempted to take pictures, not do real science. And so what we're looking at here are colored images of Mars representing certain measurements made by the spacecraft. On the left, hydrogen, then oxygen, and then measuring across the whole spectrum of the sun. And then the right is a pretty meaningless picture where they mash the 3 of those together. And so just right here, right off the bat, we can start to see what MAVEN is going to be doing, which is studying the atmosphere of Mars. On the left there, you can see hydrogen is very, very light, and it's not held particularly close to the planet. Next to that is oxygen. It's much heavier. It's 16 times heavier than hydrogen is, and it's held much, much closer to the planet than oxygen is, simply by Mars's gravity. And the same thing happens to us on the Earth. We're here breathing oxygen and nitrogen because they're heavy. There's not a lot of hydrogen in the Earth's atmosphere because, just like on Mars, it floats up to the top where it can escape. And then there's a picture here from the Mars Orbiter mission. This is the very first image captured by their camera at Mars. And what we're looking at here is the surface of Mars with a number of craters embedded in it. And this is really kind of a big moment for India, because they're really, I think, starting to sort of step out under the world stage of space exploration. They went to the moon a couple of years ago. Now they've gone to Mars. And these are the same places that the U.S., that Russia, that the European Union have been working to go to for the last number of decades, and now we can add India to that list of countries capable of going to other planets, making scientific observations. And that's really an important thing, because there's so much out there, and NASA, ESA, etc. can only do so much. We need as many countries as possible to get involved.
Now, the difference in cost in the two missions is pretty big, and I know you have a little bit of a concern.
Yeah, I'd get up on my soapbox on this one.
Yeah, I'm ready. I'm ready to allow you to just a minute of soapbox time.
That's right. So if you look at a budget proposal for one of these missions, what you find is that the vast majority of the mission is made up in labor. It's the engineers who designed it. It's the workers who assemble it. It's the scientists who operate it and take the data. The metals, the glass, etc., that goes into the mission are relatively small. And so it's been going around for the last week or so that, holy crap, this Indian mission is so cheap. And there's been comparisons to all sorts of crazy things about how cheap it is, because it cost about $75 million to launch this mission. And that's as opposed to on the order of $700 million to launch the MAVEN mission and other similar missions like Messenger. And people are like, well, is NASA basically fleecing the American public for these super expensive missions? And the answer is no. I looked up the average salary the other day for a mechanical engineer in India, and it's $5,800 a year. And you might notice that's about 10 times less than the average scientist or engineer might make here in the United States. And so it's no surprise that the mission to Mars from India costs about 10 times less as the mission from the United States. And if you look at missions run out of Europe or run out of Japan, they also cost hundreds of millions of dollars because labor costs are similarly high. So, it's a little bit of unfair, I think, beating on NASA here to say, why is your mission so expensive? When really it's costing the same amount as the Indian mission relative to our particular economies.
All right, there you go. So stop saying it was cheaper than gravity. Oh, Jason.
That's me. See?
Hello? Hello?
Hello? Hello? Oh, no, I'm not home.
All right. Well, so joining us is Ramin Skibba. Hey, Ramin.
Hey, Fraser. How are you?
Good. So don't worry. We'll get you technically caught up so that that
right.
invite somehow arrives. So why don't you just give people a quick introduction of who you are?
Sure, yeah. So I'm Ramin Skibba. I'm a research scientist at the Center for Astrophysics and Space Sciences at UC San Diego. I work on galaxy clustering, large-scale structure, sort of relating galaxy properties to their environments and to the dark matter structure. So it's basically looking at dark matter and galaxies.
Awesome.
What's my computer's giving me a reminder to do something.
Look, confirm dark matter.
Yeah. Check.
All right. So let's
yeah.
move on then. I'm going to take on the next big story, which was fun, which was the fact that black holes don't exist. So first, I'm going to let Jason pitch the story, and I'm going to let Brian tear it apart. So, Jason, tell us how black holes don't exist.
Well, I'm sorry, but there just are no black holes. It's now been proven mathematically, so we can all just put that neat idea of this, black hole slurping up all the stars and gas into nothingness, and put that aside. It's not going to send us into the past or to an alternate universe because they're just not there. At least that's how the numbers turned out for Associate Physics Professor Laura Mersini-Houghton at the University of North Carolina at Chapel Hill. She's been working on, and there's been ongoing research that she's been doing on this topic, and basically she's looking at how black holes form mathematically and coming up with a different scenario on the deaths of massive stars, where the black hole, or at least the singularity, that infinitely dense point at the center of stellar mass black holes, isn't there. It never forms, because as the star collapses, as these massive stars fall in on themselves, they emit radiation. But when they're emitting the radiation, they're actually losing mass at the same time. So a whole type of bounce back happens. The loss of mass removes some of the mass that would eventually fall in to form the singularity. Without the singularity, you don't end up with the event horizon, and you don't end up with the black hole. So that's how, or at least that's what her conclusions are coming to. And that's, that's the news that came out, is that mathematically these objects can't exist in our universe. Now, does that mean they're not there? Observationally, no, that can't be the case. But, I'm going to let Brian take it, give his spin on it, because I'm going to assume that he has a bit of a different opinion on exactly what's going on here with her findings and with what's actually out there in our universe.
Go, Brian, go.
Go, Brian, go. The first thing is, if you look at the paper, it's actually only dealing with stellar mass black holes. So the work of the paper is specifically just working on that. So it doesn't address intermediate mass black holes or supermassive black holes, which can form by other mechanisms. So unfortunately, it's one of those things where it's interesting research that then gets hyped to the point of saying, well, there is no black holes anywhere, because that makes good headlines.
What? No, that is not why we covered it. I don't know what you're talking about.
Well, let me jump in with a question. So if supermassive black holes form through a different process, I mean, aren't they basically just bigger black holes from bigger stars that have died, or scooped up more stars, so now you have a supermassive?
Not necessarily. I mean, one of the questions that's always been talked about is, when galaxies form, do they form black hole first and then form stars, or do they form stars first and then the cores collapse into black holes? And my understanding, and I'm not a galaxy expert, so it's still something that's being talked about. But the other side of this is that it's an interesting piece of work, but it's still very theoretical. To say that it's mathematically proven that black holes can't exist isn't what the paper is actually looking at. It's based upon, what it's really looking at is the consequences of what you might call the firewall paradox. And this is, you remember Hawking had said, he was quoted as saying there are no black holes, and we went through this whole thing again. And his real argument was that you can have Hawking radiation appear at an apparent horizon instead of an event horizon. So you can get what appear to be black holes but without singularities. And this whole firewall paradox is one of those things that's still somewhat controversial, because some people will say that, well, because of Hawking radiation, as you fall towards a black hole, you'd get fried to a crisp by this Hawking firewall. And others will say that, no, you won't. If you fall into just a lone black hole, you're not going to see this firewall. So there are different works that look at different things, and I think, at least the dominant consensus is that you won't experience a firewall, that you can resolve the firewall paradox when you really look at the mathematics of it. And of course, Hawking and others disagree, including the author of this paper. If the firewall paradox doesn't occur, I mean, if you don't get a firewall when you fall into it, then this is not a problem. The black holes would form the way they would normally form. If you get a firewall, what this paper shows is that the firewall could prevent the collapse of stellar mass black holes, or at least reduce the size of stellar mass black holes. So part of what's interesting about it is it could lead to some possible observational tests of whether or not there are Hawking firewalls. So if, for example, we were finding subsolar mass black holes, that we see supernovas explode, and then what we get is something that's subsolar mass black hole by some mechanism, that would lead to an idea that maybe Hawking radiation is coming into play. This is still very, very speculative. So it's interesting work, and it's cutting-edge theory, but no one should conclude from it that even mathematically or theoretically black holes don't exist.
Well, to play devil's advocate, Brian, I will say that at the end, at the conclusion of one of, actually I think it's at the conclusion of at Mersini-Houghton's most recent paper, it was stated, well, what happens when these supermassive or when these massive stars die? And she just stated, well, they just blow up.
Yes, and that's
so a black hole. So a black hole, as we know it, she is stating that it does not form, not whether or not there's a firewall paradox. It's basically there is none. There is no black hole as we would call it, as we know it.
Right. Her analytical solution, using the Hawking calculations, would say that as a star starts to collapse, that the Hawking radiation kicks in to prevent the star from collapsing into a black hole, and so it just explodes, it rips itself apart, and you don't get a black hole.
Well, would you say that there are no supermassive black holes either? Because, I mean, the evidence for the one in the Milky Way is actually pretty strong.
Right. And this is only looking at stellar mass black holes.
Okay.
So and that's part of the thing where the hype of the story kind of drowns out what is actually interesting work. I mean, Hawking has said that singularities won't form with black holes, and now you're looking at an analytical solution that shows that the collapse of a star would indeed not form a singularity under that model, which kind of reinforces Hawking's idea, which was much more terse in terms of how he approached it.
So would this basically raise the lower constraints as far as how massive a star would be to form a black hole? If you're going to say start at 10 solar masses, would this bring it up to say 30 or 40?
Well, this specific analytical solution would say no. It doesn't matter what the scale is. You don't form a black hole. Okay.
So there's no singularity. There's no point of gravitational strength there.
Right.
Nothing to crash into.
You simply cannot compress something into a black hole. From that idea. Now it's a very idealized model because she gets an exact solution. So it's an idealized model, and the other thing is it does make certain assumptions about how Hawking radiation works, and those assumptions are something that are still debated. So it's basically, if one version of a theory is correct, this is a consequence. If another theory is correct, it would have a different consequence.
So, are there black holes? Yes. Are there? But are the mechanics maybe the way we always think they are? Maybe not. So is that the takeaway?
Yeah, I think the big thing about this is that it's pushing the envelope of how we understand black holes forming, and that's something that is still being discussed and is still being researched. So a lot of people look at this like, oh, look, because some crazy scientist came out with an idea and we know it's wrong. And that's not what's true here. This is really good work, and it's interesting work. But it is also contentious work. It is work that people will argue about because it's so cutting-edge theoretical.
So does that help? I guess it doesn't really help. Like, there's the situation that a black hole is the place where the laws of physics break down, and our understanding of how that all happens, it goes away. So is it possible then that resolves that problem, in that, in fact, the universe would prevent it? It's so weird. But in fact, if you still can have supermassive black holes, then there's still some weirdness happening there.
Right, and that's one of the things we don't like singularities. We don't like the fact that general relativity goes, here's a singularity, yeah, we'll put it in a hideaway hole, but it's still there, and we don't like how the laws of physics break down there. And so one approach to that is to prevent them from forming to begin with. And there are researchers that have done that. The other approach is that somehow after the black hole forms, there can be something that can prevent the singularity while still having a black hole. It's still cutting edge stuff.
All right. Well, I'm sure we're going to revisit this about 8 more times. So I look forward to those 8
About
more
as many times as Voyager has left the solar system, perhaps.
Yep. And whether or not the Earth will be consumed by the sun when it turns into a red giant. So,
but I would add one thing. The work is far more interesting than the hype.
I'm sorry, I'm not even paying attention anymore.
Thanks.
That's great. That's great, Brian. Well, you keep us posted then, as you if you can turn that paper into something that the average layperson can understand and read, you'll be doing some of the greatest work a science journalist could do. All right, so Sandy, let's talk about SpaceX.
Okay, let's talk about SpaceX. So earlier this week on Monday, they had a groundbreaking in Brownsville, Texas. And if you don't know where Brownsville, Texas is, consider a map of Texas and go about as far south as you can on the Gulf of Mexico down to the Rio Grande, and you'll get a little town there where there aren't a lot of economic opportunities, but there is a little university there. And the reason I know about this is because there's an Arecibo Observatory user there, Rick Genet, who's been working on trying to make UT Brownsville a little more relevant in the world. And so one thing they've been doing is they've made this Arecibo remote command center there. They have something called Stargate, which is for radio observations. And this all sounds nice and fine and academic, but what's the real use here? So what they've been doing is they've been training their students there, their undergrads, to get jobs at SpaceX should SpaceX come to town. And now SpaceX is going to come to town and build a spaceport. Now let's think of this from the SpaceX side. For SpaceX, you're considering what town and maybe a remote area to build a facility. You want to be able to hire folks who live there to do work for you. You don't want to necessarily have a bunch of people move in, especially if it's a remote area. So suddenly you actually have a number of students who are already there who will be in the workforce soon enough who are trained to do work for you. So this is an excellent opportunity for Brownsville. It's right on the Gulf of Mexico, so if you do launch spacecraft and you do need a bail, you've got a nice bit of sea there. And it's I think it's a really excellent opportunity for a part of the country that usually gets neglected. So they have a project there called Stargate, and yes, it's actually called Stargate.
That is the best thing ever.
It's the best thing ever, and I forget what it stands for, but I will tell you in just a second. It's like spacecraft. It's like a tracking
and reconnaissance. Gravity.
Into gigahertz astrophysical transient emission. So you're saying gigahertz, what the heck? Well, a lot of radio astronomy happens in the gigahertz bandwidth. So Arecibo can go up to about 8 gigahertz. So that's about 3 centimeters or so in size, so about the size of a cat ear. There you are, Ms. Schmidt. There's your cat reference for the day. So they're doing a lot of you're doing a lot of radio astronomy research, but can also be tied in for spacecraft tracking. So they're training students there at UT Brownsville to be able to communicate with SpaceX spacecraft. So it's very cool. You have a lot of cutting edge equipment, and maybe they'll even be building instruments for Arecibo.
That's really cool. I wonder if it's going to be near the Gigafactory. I wonder if they're going to be in any way similar to the one for Tesla.
That's in Nevada, I think.
Yeah, the Gigafactory in Nevada is going to be churning out batteries. I think this is going to be very different. This is going to be a spaceport. So this is going to be very different than, say, Cape Canaveral or Vandenberg, and that this is going to be a commercial spaceport, very similar to the commercial airports that we go to now to fly around. That this will be something that will be accessible, and eventually, as future American Martians will be, or human Martians will be taking off from there to go colonize Mars if Elon Musk has his way for his vision of the future.
Right, and we talked about this last week, I think, that Elon Musk said that he has no plans to take SpaceX public, that it's going to remain a private company so that it can live the dream of setting up a city on Mars. Mm-hmm. And I love that as the strategy. that the whole purpose of SpaceX is to transfer human beings to Mars, and it's going to do that by making profit from doing commercial spaceflight. And so you could absolutely see this be the place 20 years down the road that you'll take your your suitcase and you'll go to Texas and you'll hop on your spaceship and you'll go to live on Mars. And this is where it's going to happen. So that's pretty
It's
exciting.
like South Texas without the oxygen.
Ouch! Let's not hate on Texas, you guys. We go there every year for a meeting.
No, I love
It's
Texas.
fine.
That is
It's
awesome.
actually a very lovely place.
Austin, Houston. I've even been to El Paso. I don't really remember much about it, but
That's cool. Okay, so let's talk about gravitational waves and the overturning thereof. Ramin.
Yeah, so actually there are a couple of people at UCSD here who work on the BICEP team. So I'll say what happened, and then I'll say what my perspective on it.
Regular viewers of the Weekly Space Hangout are pretty familiar, I think, with it, in that we've talked about it quite a bit, so you don't have to give the full-on explanation if it's going to take too long.
Yeah, so so what BICEP was doing was they were studying the B-mode polarization of the cosmic microwave background. So the E-mode polarization, or the E-mode signal was detected a while ago, and it gave sort of particularly a particular power spectrum signal which had been predicted in the past. The B-mode signal had also been predicted, and these are coming from what people call primordial gravitational waves, and those are different from, I guess, what you'd call regular gravitational waves, which people think would come from black holes, presuming that they exist, or binary stars. The issue with those gravitational waves is that they're actually very, very weak and very hard to detect. They have not been detected yet. And in fact, the B mode from the primordial gravitational waves from the early universe are also really weak and hard to detect. But if detected, they would give evidence for what's called inflation, where the universe was expanding very rapidly, and then afterwards expanding at a more normal rate. So it's a very a short period of rapid expansion. And so then there was this high-profile result, which was in all the news, that they detected these gravitational waves. Now, recently, there's been some research that suggests that maybe this quote-unquote detection was actually due to dust. And basically, in the data, in the analysis, there are a lot of systematic uncertainties that need to be systematic and statistical uncertainties that need to be accounted for, and dust is one of them. So it's possible that because of this degeneracy in the results, the dust has caused the signal that they saw, and not these gravitational waves. So for those who don't know, there's basically dust everywhere around stars, galaxies, planets. I mean, there's dust everywhere. And of course, some people call sort of small planetesimals basically large clumps of dust. And so it's kind of like you go down from particles that are really, really small up to really large dust grains and small planets. But my personal opinion is that I think maybe the BICEP people downplayed too much the effect of the dust issue early on. They wanted to have the result and get a lot of press for it, which they did. I think maybe they should have been a little more forthcoming about their uncertainties. Or they could have potentially waited later to release the results, but I'm sure they're under pressure from various places to release results at a certain time. I mean, there's always time constraints, so that is an issue. But yeah, so I think they could have been maybe a little more forthcoming about the error analysis. A lot of people aren't really interested in error analysis, but it's something that needs to be done in science. So my feeling is that it's probably not due to dust, but that it's probably a real effect. But I think that I think this is probably something that needs to be studied further, and maybe in the next year or something there will be, I hope, a more statistically significant signal that we can be sure about. But as far as we know right now, it's not clear yet.
Now, Brian, I know you did a lot of reporting both in the initial observation and the unraveling of it over the last couple of weeks. So, I mean, do you have a perspective on this?
I think if you look at the Planck data, it is it correlates well to the idea that it is that the BICEP signal is entirely dust, but it's not conclusive that it's entirely dust, and that's where you have to be a little bit careful. Some people have been saying that Planck has proved BICEP2 wrong, and that's not correct. What they've done is they've shown a level of dust at a detail that BICEP2 didn't originally have, and so my own suspicion is that it is possible that it's entirely dust, but I think it's more likely that it's probably a combination, and it's probably a stronger combination of dust and signal than originally presented by BICEP2, and that could actually be a good thing, because the BICEP2 result actually had a really strong inflation signal, kind of a surprisingly strong inflation signal, if what they said was gravitational waves was all gravitational waves. If you add dust in it and it drops the level of inflation a bit, it actually becomes more like what a lot of theorists originally expected. So this may come out to be less surprising than we originally thought and more real than some people are claiming.
Now, are they still doing observations with, I'm assuming they're still doing BICEP2 observations, and are they going to be pulling more Planck observations? How are they going to come to a conclusion as far as what the prognosis is here? Is it dust? Is it B-mode polarization? Where is it coming from?
Right. You go ahead.
I'm not sure if there's still. They probably are still taking data. I know that more analyses are taking place.
Analysis, yeah.
Yeah, and I think there is actually a lot of interaction between people who work on BICEP and people who work with Planck. That there may actually be some scientists who are involved in both collaborations. So that hopefully that'll get ironed out later. And actually, there's some disagreement between Planck and WMAP, and so on a different issue, and so there's those debates going on there. I think also Planck will at some point will release another set of results, and if you remember from the WMAP days, sometimes each set of results were slightly different than the ones in the past, and so it's possible the Planck results themselves may change a little bit too. So it's too early to say what's going to happen.
It must have been heartbreaking to be on the Planck team and to have to announce this evidence. I mean, that's how science works, but still, it must have been tough to go like, oh yeah, it looks like we can confirm that the dust could be accounting for this result. Sorry, no Nobel Prize, everybody.
Yeah.
Well, and one of the things to keep in mind is that the two different projects are doing two different types of data gathering. Because BICEP2 is looking from the ground and they're looking at a very specific patch of sky, and Planck is space-based and looking at a global survey of the sky. And so they each have advantages and disadvantages. So as they start working together, as they start gathering more data, we're going to get an answer to this solution. The question is, what is that answer going to be?
So I need to apologize. It looks like the Q&A app is busted, and this is the place where people would give us questions. At least I can't access it, so I don't know whether it's busted or whether I don't know if anyone else it says this feature is disabled, but I'm pretty sure I enabled it.
Yeah, someone was asking about that on Twitter earlier when I was in a Q&A today. Sorry, we still love you.
My fault.
You can tweet questions at me, and I might pay attention to them.
So let's move on. So I've decided unilaterally that I wanted to add a new segment to the Weekly Space Hangout, and so what happened was I've been watching the good folks at the Weekly Space Hangout Crew, and this is a community on Google+, who had formed completely independently, I guess, of all of our regular viewers and fans, and have organized themselves into this really tight-knit community, and they've been pitching stories all week about stuff that's happening in space and astronomy, and I'm like, why can't we talk about those stories?
You can.
We can. We will. And so I asked Nancy Graziano, who founded the community and has been helping us out quite a lot, to pull together her favorite stories of the week that were posted by the Weekly Space Hangout Crew. And so I thought I would take those stories and I would turn around and get some comments from the folks assembled here, and some stories that I think we missed, which is great. And then, as encouragement to the Weekly Space Hangout Crew, if you enjoy this and you want to sort of be a participant in this, please keep it up. and maybe we can figure out some way that you can funnel the stories to us in a way that we can actually get them and talk about them in a more organized fashion. So I apologize that it's ad hoc. This is just how I work. And a big thanks to Nancy for helping to organize these. So the first one is, and this was proposed by Adam Synergy, is the fact that the Philae landing date has been set. And so the European Space Agency has announced they're going to be landing Philae on 67 Churi-Guri on November 12th. And I know, Jason, you and I have been talking a bit about this over the course of the week, about how tricky this landing is going to be.
Oh, yeah. I mean, you have this object, you have this comet, and it's basically a collection of rock and ice, loosely held together. I mean, it's not like going out to a mountain and feeling this granite side. I mean, it's a rubble pile. And on top of that, it has a low density, and that means its gravity is going to be that much lower. I mean, even though it's 4 kilometers wide at its longest point, it's still a very low density object. And it's jetting, and stuff's happening as it gets near the sun. So Philae is going to have to, on November 12th, Philae is going to be deployed, and it's going to have to travel that 10 or 20 kilometers to 67P's surface. But what's going to keep it there when it lands? Why is it not just going to bounce off? Well, fortunately, Philae comes with a harpoon. Right at the base of it, as its feet touch down, that little harpoon is going to shoot into the comet's surface, and it has I guess like a hook at the end, like harpoons do, and it'll open up and keep it from flying back out into space and off into the solar system, never to be seen again. So that's the interesting part about Philae, is that not only will it land or touch down on this comet, it's going to hold on, and that's what's really going to be interesting, and of course it's going to work.
Yeah, and of course it is. But the low gravity, like, were you mentioning that it's going to be traveling at like centimeters per second,
well, that
right?
Relative Rosetta and on piggybacked Philae right now, relative to the comet, yeah, it's traveling centimeters per second. So even though they're the whole comet and orbiting spacecraft is traveling ridiculous speeds, 60,000 miles an hour or something, something silly like that through the solar system. Relative to each other, they're going, pretty slow. So, that when it touches down, it is going to be touching down pretty, it's like a feather, but still at that speed.
So it's not going to smash into the comet or something like that.
No, it is not going to be. We're going to try to keep the smashing to a minimum, because I mean, holding on at that low gravity, it doesn't take much to end up back out into space.
Yeah, just for reference, at least according to Wikipedia, the surface escape velocity from the asteroid is 0.5 meter per second.
Yeah,
from the comet. So you could quite literally just jump off the surface and achieve escape velocity. So you don't have to bounce very hard off the surface as the lander to be totally lost from ever getting back, and it has no rockets to make a second attempt or anything like that.
Oh yeah, and a hypothetical astronaut on the comet's surface could probably trip himself into escape orbit. So
that's awful.
So November 12th is going to be the day to watch it. I believe that the deployment time is just before 9 o'clock UTC, which is pretty early. I think that's 3 or 4 o'clock in the morning Eastern. So it's going to be pretty, and then Pacific time's even earlier than that. Actually, it's great for Pacific time because it's going to be late night, the day before.
That's Veterans Day, so it's a holiday.
Yeah.
But it's also, we're having a meeting here in Tucson that week of planetary scientists. It's the Division for Planetary Sciences meeting. So there'll be a whole bunch of scientists who are staying up very late that night watching.
We don't need sleep.
Yeah, so that'll be what, about midnight Tucson time?
Yeah,
right?
it's just unfortunate because I usually go to bed at 11 and conferences are hard for sleep.
That'll be a fun party.
It'll be a fun party. It'll be a bunch of Europeans.
All right, so I got another story here. So this one was proposed by Jim Meeker.
Oh, and there are questions on the event page. I don't know if anyone found that.
Okay.
People are posting them there.
Okay, all right. I will try and get those. So I'm going to move on to this one first. So this is a story from Jim Meeker, and this is a story about Nvidia I don't know if people can see this picture. Is this? No, of course this isn't working. Why? There we go. Can you see this picture?
I know
Yes.
that guy.
Yeah, so this looks like it's an image from landing on the moon, but actually this is a simulation created by Nvidia to demonstrate that all of the shadows and images that are seen on the moon are correct, moon hoaxers.
Yeah, I was going to actually talk about this in a couple of weeks when NVIDIA releases the simulation, and they're going to let people play around with it on their own computer. And so this is using sort of the state-of-the-art ability to calculate light in computer systems in terms of properly reflecting and refracting and the colors, etc., that it picks up when that happens. And so the story that I saw about this is that they were working on this for a while and they couldn't get it right, and they weren't sure what was going wrong. And then somebody who is a moon hoax debunker suggested to them that they forgot to include Neil Armstrong. They had just put the camera where Neil had been standing, but they hadn't put him there. When they put Neil in the picture, those big white suits were so reflective that it brightened the image up by something like 20%, and it was enough to fix almost all the problems that they were having with getting the shadows right and everything. And so when you put the Eagle there, that's the lander, and when you put Neil and his camera on the surface, then automatically you get all the right lights and all the right shadows, as if the sun, and if you put the sun 93 million miles away, everything just works, and that's pretty convincing evidence if something else somehow wasn't.
It's just a theory.
It's just a theory.
Like black holes.
Like black holes.
Oh, that is awesome. Okay, so I'll go another one. This comes from Helga Bjorkog, which is that ESO has signed an agreement to build moons, the multi-object optical and near-infrared spectrograph. So does anybody have any idea what I just said? Okay, well then I'm going to dig deeper here.
I like ESO. They're cool.
Yeah, I like ESO.
I think this is like a very large telescope instrument, maybe.
Yeah, so it's ESO. It's going to be attached to the to the Very Large Telescope, which is one of the ones down in Chile, and it's going to observe 10 million objects, and it's a near-infrared spectrograph. So it's going to collect light from many objects at the same time, using up to 1,000 fibers over a large field of view.
So this was pioneered by Sloan Digital Sky Survey. And so one of the problems that you have when you're making observations with a telescope is you can either take a picture and see lots of things at once, or you can take a spectrum, basically break the light into a rainbow of any one place in that picture. And so that's really slow. You can take a picture and see 1,000 stars, and if that picture takes 10 minutes, then we need 10 minutes times 1,000 to get a spectrum of each of those stars. And that's because the light interferes from each of those objects in your spectrograph. They're not particularly high-resolution instruments. And so basically what you have to do is block off the light from all the other stars to measure the one that you want. What Sloan figured out how to do was to drill these giant plates. So they start with these big metal discs that are about 1 meter across, and they machine drill hundreds of holes in that perfectly line up with all of the stars in that field of view based on a star catalog that we already have. And then you plug a fiber optic cable into each one of those holes, and then you take your 10-minute observation. And that lets you basically make 1,000 simultaneous 10-minute observations rather than having to do them sequentially. And the trade-off is that you then plug all of those into your spectrograph, and that instrument can't be as good, basically, as one that only is looking at a single object. And that makes sense. If you're trying to measure 1,000 objects simultaneously, you're not going to be able to do it as well as if you did one. But it gives a great sort of first-order spectrum of the object, and that's enough to determine things like what kind of star is this, or what kind of galaxy are we looking at? How far away might this galaxy be based on its redshift? And that tells us, is this interesting, is this not interesting? And from there, we can go back with one of these high-resolution instruments and really get the full picture.
Right.
So I've actually used a lot of Sloan Digital Sky Survey data myself and, to study the galaxies, and I agree. I mean, one of the reasons why it was so successful was because of its impressive instrument, the spectrograph. And yeah, they observed hundreds of thousands of galaxies and numerous stars as well. One issue is that you can't see two objects, or you can't. So two galaxies that are really close together, for example, they won't both be assigned spectroscopic fibers. So if they're sufficiently close together, you're basically limited by the finite size of the fiber itself. And as far as I know, I mean, since those instruments were used, the newer instruments are improving on that, or at least trying to. And so I don't know, maybe this Moon's instrument is trying to address that issue or not, but I don't know.
It seems like you would, like drilling holes in a plate and then just threading fiber optics to those holes seems like a very laborious way to go about it and not very flexible. And so you can imagine a process that's somehow more dynamic, that can somehow pull all that data from all the fiber optics simultaneously and then shut them down based on which part of the sky you're looking at. Anyway, let's move on. So Guido Bibra on the Weekly Space Hangout community posted his list of the shift changes that are happening on the International Space Station. So, and the most recent one is I guess the launch, was it yesterday?
It was yesterday.
Yeah, of the Soyuz. So Alexander Samotempo-Katiev, Yelena Serova, and Barry Wilmore launched as the second half of Expedition 41. And this is, I know a lot of people have been reporting, this is the first female cosmonaut that's gone to the space station, or gone to space in, I forget how long it's been. It's like 17 years?
I think.
Yeah.
And the first female cosmonaut to the space station ever.
Ever.
The ISS.
Yes.
Yeah. Yeah. So, good job, Russia. Although, I mean, they did launch the first female astronaut before the Americans did, so
That's right.
they still get to lord that over the Americans. Okay, so awesome. So just as encouragement to the folks at the Weekly Space Hangout crew, that was us covering your news. So if you want to join this wonderful community, just go to Google+, do a search for the WSH crew, and you'll see all of the regular names there, and by all means join in with them. Let's see. So I did find the event page, and so I think I can get a couple of questions out of here. Let me see. Sorry. There's a question about Philae, but I lost it. James Haney says, do the black holes know they don't exist? And if not, who will tell them? How do you...
If they don't know they don't exist, then they can still exist.
Yeah, how do you share that with a black hole? Very carefully, I think. Okay.
Up inside.
Right, so Andrew Planet says, how do we know if the Philae harpoon will not rebound? Do we know for certain the density of the comet's surface? And I guess this is the question, right? I mean, is it a harpoon or is it screws? I mean, what's the best analogy? Because I'm just imagining this explosive harpoon attached to the bottom of the lander, and it.
Well, I think it is a harpoon type system, but they do want to keep obviously that firing force down to a minimum as well. Otherwise, that's going to end up fighting back at you. So it is really touchy as far as is it going to work? They think that they have an idea of what's going to work best on a variety of different surfaces and different densities, but obviously 100% is not guaranteed.
Yeah, I mean, everyone has been stating again and again that this is going to be very tricky, and don't be surprised if it doesn't work. I mean,
think about how long it took them just to choose the site. They had a dozen different sites to pick from across the surface of Comet 67P. So they finally came up with site number J because of the illumination it had. So it has enough solar radiation to power Philae. And that it's safe, but yet not boring. That's the thing too. You can put the lander down in a safe spot, but you don't want it to put it down somewhere where there's really nothing to look at.
Yeah. It's I think it was described as the least worst.
Yeah.
Do you know what the mass of the harpoon is compared to the whole lander? Like, is it pretty small?
I'd have to dig around on the ESA facts and figures page.
Yeah.
So
I think the lander's 100 kilograms.
Yeah.
So
so it's
harpoon
really
one imagines would be a kilogram or so, I guess, but I don't know.
So the lander is light, so obviously this object needs to be much lighter. But then the lighter that the lander is, the less force you have to hold it into place. So I'm sure it all works out pretty well.
Yeah.
So we actually had a couple questions on Twitter. I don't know if we want to get to those.
Yeah.
One is, can planets orbit black holes? Yes, they can. If the sun was going to if the sun turned into a black hole tomorrow, we'd just know that there was no more sunlight, but our orbits would stay the same, since the orbits of things really only depend on the central mass of things are orbiting. Does anyone want to add to that?
Well, but the process of creating the black hole is going to be a very unpleasant time for the solar system.
Yes. Yeah.
Is the sun even going to form a black hole?
No.
I don't think
right? Yeah, it's been a while since I've done.
We found pulsars though around
And the other question, is that could rainbows form the plumes of Enceladus, and that you could technically see rainbows and are they water droplets? Right? Are they water droplets? It's water.
They are until they freeze.
Right.
Then they're ice droplets.
But you can see rainbows and ice particles in our atmosphere, right?
Mm-hmm.
So
yeah,
I guess
I think
you
it's
could
probably
see
a
them, but
density
they'd probably
question.
be very faint, and it would tell you about the size of the particles that you're seeing the rainbow in.
Would you see, though, a rainbow, or would you see a halo? Like, would you see the light coming through the ice particles and turning into like a sundog?
Yeah, perhaps.
Yeah,
You could probably get a glory effect though. Because they've seen that in Venus's atmosphere with Venus Express. I don't think it was an optical light, but I'd have to check on that. But depending on the angle of where the sun is relative to the viewer, you might be able to get that, because a sundog is obviously close to the sun, but then a glory or a rainbow is going to be where the sun is opposite you.
Mm-hmm.
So you might have it. I mean, it'd be really interesting.
Yeah, I propose the Enceladus Rainbow Explorer mission.
I mean, you could probably see it with your next Titan or your next Saturn mission, but you would probably need a really long exposure time to see it, just because you're so far away from the sun, and I'm not really sure how concentrated the ice particles are there.
Yeah,
it's very diffuse. That's the biggest problem. You're talking about a very, very low density compared to the Earth's atmosphere, and even much lower than, like, say, the Martian atmosphere in terms of the density of your particles.
All right, well, we better wrap this up. We're running the end of our hour. Want to give everyone a chance to let us know where we can find out more about them. So, Sondi, where do we find out more, Sondi?
I am at Sondi. I should probably write that right above my head. I'm at Sondi on Twitter, and I'm also at Observatory Cats if you want a cat rescued by a genuine astronomer in the Tucson area. We've got plenty. They're just not at my house.
Brian, where do we find out more?
You can find me on Twitter at Brian Koberlein, and you can find me on my website, briankoberlein.com.
Awesome. And I'm starting to see your articles picking up all over the place.
Yeah.
Phys.org and Science Daily, things like that. So, Jason, where do we find out more?
I'm on Twitter often at JP Major. I also have a Facebook page, Lights in the Dark. My website is Lights in the Dark, and when I am writing, when I have the time these days, I'm at Universe Today and on Discovery Space News.
Awesome. Morgan, where do we find out more?
Yeah, you can find me on Twitter at Morgan Rehnberg, on my website, cosmicchatter.org, and right after this, over in the Google Plus Space Hangout, where I'll answer all those questions that we didn't have a chance to answer with our little snafu here.
Right. So once again, go to the Google Plus Space community, which is different from the Weekly Space Hangout community, and Morgan will be there and throw some zingers at him.
Yeah, and then I will redirect them to this fine panel.
Awesome. All right, and Ramin, where do we find out more?
So I'm on Twitter at Ramin Skibba, so that's RaminSkibba, and I'm blogging at raminskibba.net.
Awesome. So I want to remind everyone, and of course I'm FKN on Twitter. You can find me all over the internet. So I just want to remind everybody that we're now sending out the Weekly Space Hangout as a audio and video podcast, so you can just download the audio podcast wherever your fine audio podcasts are found. We'll have a link from on iTunes. You can get a link. I'm not sure what the actual link is. I think it's universetoday.com/audio. Anyway, but I should know this. But I've got a question for people, which is, does anybody use the video version of the podcast? So not the YouTube version, but the one that we actually upload that you download to your phone or your mobile device every week. So if anybody does, drop me an email at info@universetoday.com. And my feeling is that nobody does. That this is not to be. This is the kind of thing you'll put on your headphones and you'll listen to while you're working out, or driving, or doing your commute. But you won't be watching this on video. So if nobody does, we probably won't need to do it anymore. We'll just keep doing the audio version. So that's awesome. So once again, thanks everyone. Thanks to the Weekly Space Hangout crew for participating this week. We really appreciate all of your hard work. Thanks to everyone who joined us, and we'll see you all next week. I'm going to press stop broadcast now, but Ramin, you should stick around. Don't leave yet, because I want to show you how to get the cool little thing at the bottom of your window.
Okay.
All right. Thanks everyone. We'll see you all later.